Okay, welcome everybody to 4.7, inverse trig functions. So we are going to look at sine, cosine, and tangent, only in this case we are going to look at sine inverse, cosine inverse, and tangent inverse. And you see this here, this little statement says arc sine, arc cosine, arc tangent. This is the same thing as sine inverse, cosine inverse, and tangent inverse, respectively. And you can find these buttons on your calculator. They're right above your sine, cosine, and tangent buttons. They look a little bit like, actually I have my pen with me today. So I have tan inverse, I have cosine inverse, and I have sine inverse. One of these things you just have to remember is that this -1 does not represent a -1 exponent. Okay, these things are completely different than 1 over sine. All right, so this is kind of our undoing functions, right? Because that's what inverse kind of means. So we're going to look at our domain and range. We're actually going to graph these three inverse trig functions, and we're going to look at some compositions. So first of all, let's just kind of do a refresher over what we know about inverse functions to begin with. We've done a lot of this already a few weeks ago, quite a few weeks ago actually, I guess. So there's a horizontal line test that we need to do. So in something like this, if we drew in a horizontal line, it tells us that it touches twice and therefore has no inverse. But there are ways that we can make inverses, and that's what we're going to get to. Or if we had something like a cubic function here, this particular cubic function, the horizontal line test is fine, which means it has an inverse that we can find pretty easily, actually, in most of these cases. So this is what I was just talking about. If I have one intersection, then it has an inverse, and more than one intersection, it has no inverse, kind of. There's ways that we can make inverses, and it has to do with only looking at part of the graph or parts of the graph. I hope most of you can fill in this little blank spot without my help. However, because I got to fill this stuff in for everybody, inverses are reflected over the line y equals x. So if I took this quadratic function and I reflected across the line y equals x, I would get something along the line of this sideways parabola, which would show that there's no function, but we can limit it so there is a function. That's what I'm getting at. So this is what I was just saying. Does the graph of x squared have an inverse? And if we look at the graph initially, we would say no, because it fails the horizontal line test. However, we know that the inverse of the square is the square root. So it means there is an inverse because they undo each other. But we know that when we square root an equation, we get both plus and minus because there's two different parts to the equation. So what we like to do is we like to limit the graph to maybe only this half, the positive version. And then we could limit it to the negative version and get a different graph. And that's why you can't graph this sideways parabola on your calculator unless you say it's the square root of x and in two different equations, the negative square root of x. Then you could actually graph what would look like a sideways parabola because it's two different equations. So let's start with arc sine. And so you notice my little mentioning here, sine inverse, that's sine to the -1. Please don't say sine -1, okay, because that has no meaning to us. The meaning to us is sine inverse or arc sine. That's all you're allowed to say in this stuff, in this particular lesson. And I don't care which one you use, whichever one you like to say better. But I will tell you that the sine inverse, this left one, is the one that's on your calculator. And it will come in handy in the 4.8 lesson. All right, so what I want to do is I want to look at one full period of the graph of sine of x. So one full period. I hope all of you guys can sketch that. You can just kind of do it top to your side of your paper there. One full period of the graph of sine of x does not have an inverse because it fails this horizontal line test, and it fails miserably because it fails to infinity. There's always going to be more and more lines over here, more and more intersections. So we know that there's no inverse, but I'm claiming there is because we're looking at this function sine inverse. Well, here's what we have to do. We have to limit the domain in order to get the entire range. So I'm going to erase this picture here. I'm going to try a little bit different. I'm going to try a different one period of the function to kind of hope we can visualize what's going on here. I'm going to go this way. I'm going to go full period this way, and I'm going to go full period the other direction as well. You'll get to see why in a second. All right, so there's two full periods. And then the question is, where can I limit this graph in order to get the entire range? Well, we know the range is from -1 to 1. So if we put this in here, this would be -1 and this would be 1. We know this already. And there's all sorts of spots where we could limit this. We could say, oh, let's go from here to here. This would get an entire range of +1 to -1. The thing is, we like to do things near or close by to the y-axis. So this is a little bit far away, so I don't really want to do that. I want to kind of get rid of those. So let's do stuff around the y-axis. This means I can start back here and get the -1 and go up the graph. Can go up the graph up until +1. So this little section right here is a representation of all range values for sine of x. And I hope you know that this is pi halves and this is -pi halves. So we're going to limit this graph of sine of x down to down to -pi halves to +pi halves. And I'm going to get rid of that, and I'm going to get rid of that. And we're going to limit it to just this portion of the sine curve. But then we have to think about, okay, this is sine of x still. So now I want to reflect it across the line y equals x. And if you remember, the domain of the original becomes the range of the inverse. And the range of the original becomes the domain of the inverse. So let's clear this. Let's kind of take a different representation of this. Let's go ahead and look at, oops, let me go back over here. Pen, red, okay. So here's our limiting from sine of x. So here is -pi halves. Here is pi halves. -1, 1. And we know our graph kind of comes up here like so. It's kind of ugly, but I think you get my idea. Get my drift. Well, the reflection across the line y equals x my range values become my domain values. And my domain values become my range values. And remember, I'm trying to graph this new function, so I got to figure out how this function is going to work. I know I have the point over here that is pi halves comma 1. So I get the point 1 comma pi halves right up in here. The point 0, 0 stays the same. And then I get the point -1, -pi halves from that inverse as well. And then you have to be careful. You don't want to graph it in the same motion as the sine curve. It actually goes in the opposite motion here. Rather than going up and down like this, it actually is going to start down and here. Now you'll notice I did not put any arrows anywhere, and that's because this function actually stops at those two dots because the original function over here stopped at those two dots. So this graph here is y equals sine inverse of x. You'll notice my domain is now -1 to 1. My range is negative pi halves to pi halves. Okay, I'm going to get rid of these graphs here, and I'm going to go on to whatever else I was planning on saying here in my PowerPoint. You know how I work. Okay, so we get all of our range values. With the new limited function, we swap the x and y. We graph our reflection. That's our new graph, and I've just basically everything that I said just a few minutes ago, now it's just written down so you can kind of see it and see what I was saying. This right here is very important for us a little bit later. It's coming up, and it has to do with quadrants again, so there's quadrants that we have to be careful of that we're dealing with. We can only do sine inverse for quadrants 1 and quadrants 1 and 4, because that's where these angles are between negative pi halves and positive pi halves. If I was to draw that on the circle, I'd only be going this way. This is negative pi halves, and this is positive pi halves. All right? This is the only spot where sine inverse works. All right, so let's move on to cosine inverse. This one won't take as long because we've kind of got the basic idea from sine. We can figure out cosine inverse, I think, pretty quickly. So same as sine of x, we need to limit the function. So if we think about one period of cosine, it's kind of an ugly graph of cosine, but you get the idea. -1 to 1. And if we start at 0, and we want all of the range values, we can start here, because that would be a positive one, and we can go down to here, which would get everything from 1 to -1, so I can get rid of this now. And I hope you know that that is, oops, not pi halves, it's pi. So that means we're going to limit the domain of cosine of x into 0 to pi, and we're going to go from -1 to 1. And we'll get all this written out here on the PowerPoint in just a second, but let's take a look at what that's going to look like graphically for the graph of the cosine of the cosine inverse of x. Now, here's the thing. We need a -1 and a +1 on the x-axis because the reflection there. And then I only need 0 to pi, so I kind of drew my graph kind of ugly, so I'm going to change that. I don't need any negative numbers for cosine inverse. So I need to go from 0 to pi, and going from -1 to 1 in that direction. And now I'm just going to plot some points. I know that at 0, 1, so I have the point 1, 0. And at pi, -1, so I'm at the point -1, pi. I also need the halfway in here, I guess, so that's pi halves. And the fun thing is always trying to figure out what direction should I be graphing. And it's going to be like this. Oops. See if I can do this well. All right. So obviously this little thing doesn't exist, but you get my idea. And again, no arrows at the end of these graphs. Now I won't be asking you to graph these functions really, but you might be able to figure out some transformations given the equations. And the transformations still work the same. Vertical stretch, horizontal stretch, translations, transformation, that sort of stuff. They still work the same way in any function that we deal with. Okay, so this is the graph of y equals cosine inverse of x. All right, notice domain and your range here. So I'm gonna eliminate, I'm gonna put up here on the PowerPoint exactly what I was just talking about. And I'm gonna point out that 0 to pi represents, this interval from 0 to pi represents quadrants 1 and 2. And you should know that from your unit circle. All right, last one. Tan inverse is actually a pretty simple one, even though it has to be different. You'll notice here, if we were to graph tangent of x, I have an asymptote, and I have an asymptote. And you remember we're just graphing one period. We don't have to deal with all the periods here, but if I graph one period, negative pi halves to pi halves, let's see, we have the point there, there, and there, and we kind of get this cubic looking thing this way. And if you look at just one period of tangent, there is no need to limit it because the horizontal line test works perfectly. We are limiting, technically, we're limiting the entire graph down to one period, but we can just think about this entire thing as this little piece here is just the entire graph. And if we were to take the inverse, different color here, so we go up here to pi halves, and we go down here to negative pi halves. Well, those asymptotes have to come along, so those vertical asymptotes become horizontal asymptotes. And that one there as well. And then you can think about this 1 and this negative 1. And if we were to just swap some points here, positive pi halves, positive 1. 0, 0. Negative pi halves was negative 1, so we go this way. And then we get what ends up looking almost like a cube root function. And that should kind of make sense because the inverse of a cubic is a cube root. So since tangent looks like a cubic, its inverse needs to look like a cube root. All right, so this is tan inverse of x, obviously equals to y. All right. So we use these inverse functions to actually solve for angles. We can solve for angles here. I'll show you what I mean here in just a couple minutes. Okay, so those are my graphs. Let's eliminate the pictures and kind of go through what else I was talking about here. The domain of tan inverse is all real numbers. And the range, notice that there's no brackets here because they're asymptotes. The range is from negative pi halves to pi halves. And again, tangent here exists in quadrant 1 and 4. Tan inverse exists in quadrants 1 and 4. And again, remember, that's going to be very important to us. Okay, so we're going to be solving for angles, basically. I could say something, actually, I'm going to write it right up here. We're going to think unit circle, and we're looking for sine inverse of 1/2 equals to y. Now, here's what we have to understand, that if I was to give you y equals sine of theta, and I don't know what theta is, what I can do is I can take the sine inverse of both sides and say sine inverse of y is equal to theta because the sine inverse and the sine cancel out. So this is how we're going to be using this. We're going to be solving for theta. So this particular question that I have written out here is sine inverse of 1/2 equals y. And we're going to think about the unit circle, but I'm going to think about this in the other form. I'm going to say, well, sine, and this is how some of you are going to think about this, sine of what angle equals 1/2 using my inverse property? Well, here's where you have to think about your unit circle. There's not only one spot where this occurs, technically, right? So sine inverse of y equals to 1/2. And you have to think about the range. First of all, you have to think about the range of sine inverse, but we'll get that in just a second. Sine inverse, or sorry, sine of what angle is equal to half? Well, that could be y equals pi sixths, which is 30 degrees, by the way, but I like to get you guys familiar with radians. Or the other angle is in quadrant 2, which is 5 pi 6. But here's the thing, that's not both of these are not the answer. Because we're dealing with sine inverse, the range of sine inverse was negative pi halves to positive pi halves. So it's quadrants 1 and 4. Now here's the thing, 5 pi 6 is in quadrant 2. So we're looking at y equals, we're looking at y equals only pi over 6. Yes, you can write 30 degrees, but really try to become familiar with your radian measures. Okay, what about cosine inverse of root 2 over 2? So again, you're asking yourself, cosine of what angle equals root 2 over 2? Well, you should be able to look at your unit circle and find the x-coordinate with a positive root 2 over 2. Well, positive root 2 over 2 is going to occur at pi fourths, which is 45 degrees, but it's also going to occur somewhere else. It's actually also going to occur at 7 pi fourths in quadrant 4. But cosine inverse doesn't exist in quadrant 4, so this doesn't work. So my only answer is this. What about sine inverse of pi halves? Notice I didn't put a y here, but I should have. Now this one's tricky because some people are just going to say, oh, I can just plug this into my calculator. Go ahead, but see what happens. And if you plug this into your calculator, you should get an error. And here's the reason. You have to actually do a little bit of thinking before you just go and do it. Pi halves is approximately equal to 1.57. Well, here's the problem. The domain of sine inverse is only from -1 to 1, so this is outside the domain, and therefore has no solution in this particular question. So this one's like my little tricky problem. Okay, so sine inverse of pi halves does not work. It's just like if I was trying to say sine inverse of 2. That doesn't work either because it's outside the domain. What about just plugging things in? This is just calculator stuff. So arc sine of 0.35, arc cosine of 2. What you're going to notice, I'm going to do something right here that you might not really like for me here is let's go sine inverse of 0.35. And initially, I get 0.35. Let's go 76. But maybe your friend got 20.4873. So why are you getting two different answers here? Because this is a function, you're only allowed to get one answer. And the reason is because it depends on your calculator. It depends on the mode you are in. In the first answer that I gave, I was in radian mode. So my answer is 0.3576 radians. Whereas my second answer was in degrees, so this is actually 20.4873 degrees. They are the same exact answer, but you need to know what your calculator is in to determine what your calculator is giving you. All right, and the last one, hopefully you actually know this already without plugging it in your calculator. This is no can, okay? Because cosine domain, or arc cosine's domain is from -1 to 1. You can't plug that in. Try plugging it in. You get error domain, and value entered is not allowed in the function or command. Okay, you're not allowed to do that. All right, still got a couple more things to go here, so just kind of hang with me here. Couple important things that come up with sine or the inverse functions is these three statements are always true as long as it's a defined answer, so no undefined stuff, basically. So notice these are compositions. These compositions are always true, these canceling each other out sort of things. But we also get this. This is only true the other way. Notice this is inverse of the original function. This is only true if x is in the restricted domain. So in this first one, x has to belong to the interval from negative domain. So negative pi halves to pi halves. In the cosine one, x has to belong to the interval from 0 to pi. And for this one here, x has to belong to the interval from negative, actually open parentheses, so let's delete that. Belongs to negative pi halves to pi halves. Most of you will probably not be familiar with this symbol. This means belongs to. It just means that x is in this interval. All right? It's the only time that this works, but here's a problem. So here, sine inverse of sine of 5 pi 6 does not equal 5 pi 6 because 5 pi 6 is not in this top interval here from negative pi halves to pi halves. However, there is an angle that we could actually answer this with. And we should know that the sine of 5 pi 6 is equal to the sine of pi 6. And if you look at your unit circle, you can verify this for yourself. Both of the y values are 1/2. So we can change the angle to part of our domain so we get the same y value. But we can say, this is what I'm saying here. Sine inverse of sine of 5 pi 6 isn't possible until we change the angle. And now pi 6 is inside my restricted domain. So my answer is pi 6. Okay, some of this stuff is going to get a little challenging here on this particular page. So what if I was to give you something like the cosine of sine inverse of 1/2? And just like with any type of problem, you usually work with the inside out. So what we're going to do is we're going to say, well, let's start with sine inverse of 1/2 equals to theta, because in this inverse stuff, we're always solving for an angle. Well, in this particular case, sine inverse of 1/2 equals to theta tells me that theta, or sine theta equals 1/2. We did this already. And that means theta is 30 degrees, or pi 6. Well, this entire thing, maybe we'll circle this. This entire thing is theta, which means I can now replace what I know for theta for cosine. So I can say now I get cosine of 30 equals root 3 over 2. Pretty straightforward. What about sine of cosine inverse of x? This is where it gets challenging. So same idea as before. This means cosine inverse of x equals theta. So we can say cosine of theta equals x. And we're going to actually create some right triangle stuff here. Oops. If I said theta was right here or up above, I don't really care. This tells me that the cosine of this angle is x, or x over 1. So since I know cosine is adjacent over hypotenuse, I'm going to put in what I know. Now, I want to eventually find sine inverse of theta. Or not sine inverse, goofball. Sine of theta. And that's from this statement right here. I want to find sine of theta. Well, in order to find sine of theta, I need to use the opposite side. Well, pretty simple Pythagorean theorem states this side is equal to the square root of the hypotenuse squared minus the adjacent squared. Which means the answer to this question is the sine of cosine inverse of, oops, not theta again, of x is square root of 1 minus x squared all over 1. Because now I want to find the sine of this angle. Sine is opposite over hypotenuse. It's not a challenging concept as long as you know how to use the Pythagorean theorem and know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. These problems are pretty simple, pretty straightforward, I think, but they always give students troubles. All right, so here is kind of a lineup of the next 2 weeks for you. Monday, we want to do the 4.7 section. Wednesday, we're going to do 4.8. I'm going to make a video for that, but it's going to be only examples because they are all word problems. So that's our word problem, kind of real-world examples for using trig. And I also want you to start your review. Hopefully, some of you guys actually try to get ahead a little bit so you can start your review early. We are going to have kind of an in-class review sort of thing going on. Obviously, not much of me doing anything as normal. Oh, that's on Friday. We're going to quiz on Thursday. Missed that. And then Monday and Wednesday of, that would be the week of, what is that the week of? That's the week of Thanksgiving. So Monday and Wednesday, the only 2 days that I see you, we're going to do our test. It's a 2-part test. One part is all of the algebraic stuff, and the other part is all of the graphing stuff. So you guys have a lot of studying to do over the next 2 weeks, so good luck. Have fun with this section, and go ahead and start 4.8 as well. I'll go ahead and do a video for that coming up.